Hello there and welcome back. Technically, this is the first episode, so there's no point in saying that. But yeah, today we'll be looking at the first topic under the IGCSE Chemistry 0620 syllabus, that being the states of matter. Now, I'll be following the syllabus order for all of these, so do keep that in mind. So, Unit 1, or like 1.1, I guess, would be the states of matter, those being, of course, solids, liquids, and gases. Now, one thing that all of these have in common is that they are forms of matter. Matter is anything that's made up of molecules and atoms. And the main thing you need to know here is the properties for each of these. So, solids, things like your tables, chairs, you yourself are a solid. You guys have a fixed shape because the atoms are really close together, and you have a fixed shape and volume because again the atoms are close together and there are strong intermolecular forces of attraction. Similarly, they cannot be compressed, right? That's only something that gases can do. We'll look at that later on. But yeah, they can't be compressed. And that's about it. When you look at liquids, let's just get that on here. Liquids are, okay, first off, they have weaker forces of attraction between molecules, at least when compared to solids, which means that while they have a fixed volume, so 5 centimeter cubes of water is still 5 centimeter cubes of water, their shape is actually variable. They do not have a fixed shape. They take the shape of the container. So think about water and how it changes shape. Yeah. You can tell this is my first video. I'm really nervous. But anyway, okay, this is an important distinction. They have a fixed volume, but the shape is changing. So keep that in mind. And because their shape is variable, you could say that they're capable of flowing. Again, think of water and how it can flow. One important thing is that water isn't the only liquid in the universe. A lot of people, when they hear liquid, they automatically assume water. And when you get to the future chapters, that can be a very problematic way of thinking. So keep that in mind. I'm really nervous. Then you have gases. Now, gases do not have a fixed shape, no fixed shape or volume. This is because amongst the three states of matter, they have the weakest forces of attraction between the molecules. Now, there's always that one kid in class that points out the fourth state of matter, plasma. If you're that person, please leave. I'm joking, of course, but yeah, anyway. So this is an important thing again. And I mentioned this before, but they can be compressed. Again, because of the weaker, there are almost no forces of attraction, which means that they can, words, English. Yeah, they can be compressed. Those are the properties. Let me just take a breather. I'm really nervous. Right, okay, I'm back. Usually that would be enough social interaction, but for me, but whatever. The next thing that you need to know is how the states of matter can transition amongst themselves. Now, this first topic is honestly kind of simple. We've all been learning this since third grade. So I think this should be relatively quick, assuming I can draw it fast enough. So you have solids, uh, liquids, and gases. Let me just bring that down here. Nope, that didn't work. Yeah. Right. Um, you can transition back and forth between each of these states, I guess. So let's draw some arrows to denote that. Now repeat with me, kids. As you go from a solid to a liquid, that process is called melting. Liquids to gases would be evaporation. For those of you that said boiling, that's actually not the same thing as evaporation. It's going to sound bad, right? I'm going to make myself look bad here. I'm not sure if the distinction between evaporation and condensation is like something that's part of the chemistry syllabus, but those of you that do physics should know the difference from having done thermal physics. But anyway, as you go from a liquid to a gas, that's called, a gas to a liquid, that's called condensation, right? And finally, from a liquid to a solid, that's called freezing. Again, this is a basic thing, we've all done this. Let me add a few more things here that the syllabus doesn't require, at least to my knowledge. This, the direct conversion from solid to a gas. So, like, for example, from dry ice to carbon dioxide would be called sublimation, right? And if I were to go directly from gas to a solid, that would be desublimation, or I prefer to call it deposition. Deposition. Let me just double check if that's correct. Yeah, don't worry, I'm right. Deposition is correct. Uh, that's not a good thing, right? It's not a good thing that I had to Google that. Okay, according to the syllabus, you also need to have some knowledge about. Let's just double check here. Right? So we talked about the distinguishing properties between the states of matter. We kind of went into the structure, and let's be honest here, we all know the structure and motions. Solids vibrate, liquids can flow, and gases can travel long distances. I mentioned the forces of attraction. Solids are arranged in a regular lattice. Gases are far apart, and liquids fall in between the two extremes. I mentioned the changes of state. I think you can just take water as an example here, where if I have ice can change to water at 0 degrees Celsius. That's its melting point. Water changes to a gas, in this case steam, at 100 degrees Celsius. That's its boiling point. Condensation is the opposite of evaporation, and melting is the opposite of freezing. That's just like a niche thing that you need to know. And again, at least in the case of water, the freezing and melting point is the same, that being 0 degrees Celsius. Yeah, and I still feel nervous, but we'll get there. Now, again, according to the syllabus, under 1.1, solids, liquids, and gases, you also need to describe the effects of temperature and pressure on the volume of a gas. So that's the fourth thing we need to do. Let's just do that. So RTP also known as STP. So room temperature and pressure, or standard temperature and pressure, they mean the same thing. Basically means that the temperature is 20 degrees Celsius and the pressure is 1 atmosphere. Right. So at STP, okay. So at STP, gases behave like gases. They're kind of normal, if that makes sense. Whereas if I start increasing the temperature, that's going to have an effect on the structure, the forces, and the arrangement of the gas molecules. It's going to have an effect on the molecules of all states of matter. But it's, I guess, like, yeah, you need to know about it in gases the most. So as temperature increases, I'll just give you a general description here. As the temperature increases, so as this increases, the particles, they absorb more heat energy, so they have more kinetic energy. In the case of solids, they vibrate more. Remember, solids display vibrational motion. And in the case for liquids and gases, they move larger distances. Yeah. And this means that for all three of them, they undergo thermal expansion. Again, for those of you that are doing IGCSE physics, you should be, well, at this point, you should be familiar with this term from thermal physics. But it's basically just an increase in volume, if that makes sense. Now, eventually, when you reach the melting point of a substance, you see the particles are able to overcome their forces of attraction, which is when you see the change of state. Right. Do you guys remember the difference between evaporation and boiling? Yeah, that's part of the chemistry syllabus. That's my bad. Okay. That's embarrassing. I just got like a call. Anyway, so you have evaporation, right? Evaporation. And then you have boiling. There are two main differences. Boiling occurs at a specific temperature, that being the boiling point. Specific temperature. So boiling is the change of state from a liquid to a gas at that liquid's specific boiling point. Temperature. Whereas evaporation is a change of state from a liquid to a gas at all temperatures that are below the liquid's boiling point. So it doesn't occur at a specific temperature. Another difference is that boiling occurs throughout the liquid. It occurs throughout the liquid, whereas evaporation only occurs at the surface of a liquid. So what that means is if I have a container here, eventually the particles that are at the top will have enough energy to escape, while the particles at the bottom, which have relatively less energy, still remain in the container. So it only occurs at the surface of the liquid. Yeah, that's the main difference between evaporation and boiling. Another important distinction that I want to make when it comes to a change of state occurring in matter, the stronger that the forces of attraction are, the more heat energy you need to overcome them. So in the case of solids, they generally have higher melting points because they have the strongest forces of attraction, while gases usually have lower melting points are like they have lower melting and boiling points because they have lower weaker forces of attraction. This is taking a toll on my anxiety. Um, just give me a second. Right. Do you guys remember how I mentioned that the melting and freezing point for water, which is 0 degrees, is the same? So similarly, uh, the point, the temperature at which water boils and condenses is also 100 degrees. Or rather, once you reach 100 degrees, it begins to boil. And once water goes below 100 degrees Celsius, condensation begins. Okay. So next we come on to heating and cooling curves. This is a pretty this is one of my favorite topics. Let me just go to a new page real quick. So heating and cooling curves. Let's just start doing this. Let me just try and draw a graph. I'll try to script the next video, that might help. Maybe not. Yeah. I get really nervous this happens. But I do hope I can at least impart some knowledge onto people. So, if we begin as a solid, this area would be as a liquid and a gas. Now, at the y-axis, we have the temperature. The temperature as degrees Celsius. Over here we have the time. Let's say it's in seconds. So, as I heat a solid, up to a certain point in time, the temperature of the solid will increase with heating. But once I reach the melting point of that solid, the melting point, of course, is this area right here. Once I reach this melting point, for a set amount of time, so from here to here, whatever duration of time this is, the temperature of the solid will remain constant, regardless of whether, it will remain constant, but it will still, even if it's still being heated. So, for this duration of time, the temperature won't change until you come here, because all of the energy that's being put in via heating is being used to overcome the forces of attraction. Thus, melting occurs, and which is why you don't really see a change in temperature. Now, as a liquid, again the same process occurs. The same process occurs where, again, for a set duration, from here to here, the whatever material you have will remain as a liquid, and if you continue heating it, the temperature will rise up to this point where you reach its boiling point. So in the case for water, that's 100 degrees Celsius, and again for a set duration, the temperature will remain constant, and that constant temperature will be the boiling point. So, and the reasoning is the same. All of the energy that you're putting into the matter via heating is being used to see the change of state rather than an increase in temperature. So, until a gas, all of the matter has become a gas, there won't really be a change in temperature. So, let me just write those down. You're melting here. So this constant value thing denotes melting. This denotes, let's just say it's boiling. Yeah, it is boiling, sorry. And because remember, it's occurring at a specific temperature. Whereas any time between this area, you could say this is evaporation. So at any of these temperatures, which are this range of temperature that I just drew, it's all of these are like below the boiling point of the liquid, which is why evaporation can still occur. So you can still see a change of state from a liquid to a gas, but it's not via boiling, it's via evaporation. That's an important distinction that you need to take note of. Um, let's just go through the textbook and check some things. Right, I think I mentioned everything for this heating curve. Now I need to talk about the cooling curve, which is just the thing, which is the same thing, but it's the other way around. Right, so this is a cooling curve. Again, it's basically just the heating curve, but upside down. One thing I will say, notice how this point right here, it doesn't touch the axis because, well, okay, wait. Yeah, it doesn't touch the axis, and that's just something you need to keep note of. Whereas this point here touches the x-axis because the solid can be at 0 degrees Celsius or even below that in some cases. Now, again, the explanations are kind of similar. This point here denotes condensation, right? So condensation occurs at a constant temperature. In the case for water, that's 100 degrees Celsius. As you go from a liquid to a solid, that's called freezing, and it occurs at 0 degrees Celsius for water, not for all liquids, specifically for water. The explanations are the same. So as the gas cools, the particles will basically move less quickly and with less energy. So they collide very little, and eventually the intermolecular space between particles will begin to reduce, and you see a change of state from a gas to a liquid, and eventually movement will cease altogether, and well, there will be vibrational movement, but actual locomotion between particles won't really occur. I'm using some fancy terms. And so, yeah, that's when freezing occurs. So, really, you can say that a lot of these explanations are just using the same terms. It's just a matter of how you order them, and you're just changing a few other words such as increase or decrease, or yeah, I mean, that's basically it. Now, okay, note, this is important. These, you can see heating and cooling curves. They were mainly composed of straight lines rather than actual curves. That's because with pure substances, so if I have distilled water, which is pure H2O, you're going to see a curve similar to this. But in nature, a lot of substances are impure. So a lot of heating and cooling curves won't really have straight lines. Rather, they'll have sharp melting and boiling points, and because of the impurities inside them. So that's an important thing you need to keep in mind. Now, because impure substances won't really have specific melting and boiling points, rather than seeing a straight line such as this, you're going to see something like this, where condensation occurs at a range of temperatures from here to here. And again, the same thing with freezing, rather than having a straight line, you'll see something like this, where between this and this range of temperatures is when freezing would occur for impure water. And you could apply the same logic for a heating curve. So the next concept that we'll be looking at here is gas pressure. So again, if you do physics, I'm assuming most of you do physics, you would have done this it's part of thermal physics. So it shouldn't really, it's even as long as you've done checkpoint, it's not going to be that hard. The main thing you need to know is that if I have a container of gas, if I raise the temperature, the pressure increases because the molecules of gas will gain more kinetic energy to move about and collide. They collide with more energy, and so more force will act per unit area on the surface of the container, resulting in more pressure. So that means that pressure is directly proportional to temperature, right? I think that's simple. The same thing is applied to the volume. So if I were to, let's say, reduce the volume of the container, right? If I were to reduce the volume, that means that the same number of gas particles are forced to occupy a smaller space, which will result in an increase in the number of collisions. The energy of particles will still remain the same, but the number of collisions will increase against the container, against the walls of the container, and against each other. And so more force will be applied per unit area, resulting in a higher pressure. That means that pressure is inversely proportional to volume. Again, if you do IGCSE physics, this is the basis for Boyle's law, right? It's not exactly Boyle's law. Boyle's law is P1 V1 equals to P2 V2. Don't worry about that. But that P1 V1 thing is derived from this relationship. So, yeah. Right. So now we have made our way to diffusion. So, diffusion is really just the movement of particles from an area of higher concentration to an area of lower concentration as a result of their random movement. The best way to explain this would be if there's a naughty student in the class that decided to cut the cheese or let one loose at this corner, particles, there'll be more, I guess, order particles, for lack of a better term, over here. But as time passes, these particles will randomly move around the class. So, for when he first lets it loose, this area of the class is the area of higher concentration, while I guess this area is the lower concentration area. But as time passes and particles move about, you'll see that the particles are evenly distributed. Thus, they have moved from an area of higher concentration to an area of lower concentration as a result of their random movement. And that's something that you would learn in IGCSE biology. I'm pretty sure that's the second or third topic. It's the third topic. It's part of the third topic. Yeah, I mean, that's more or less the main, I guess, definition and concept of diffusion. But now we must consider the rate of diffusion in gases. So diffusion can occur in solids. It cannot. So if I have salt water, it's eventually going to dissolve and diffuse. I don't think that example is correct, but it can occur in solids as well. Diffusion in water is called osmosis. Osmosis is just a special type of diffusion specifically for water. You learn about that in biology, but don't worry about it right now. So, the main thing I want to highlight here is an experiment that compares the rate of diffusion in gases. Let me just draw the setup real quick. Right, so I have the setup right here. Basically, you have a glass tube that's blocked on both ends, and I place two balls of cotton at A and B. At A, I have cotton that's been soaked in an ammonia solution, and it gives off ammonia gas in this direction. And on the other end, I have cotton soaked with hydrochloric acid, which gives off hydrogen chloride gas at this end. Now, the main thing that you need to know here is that when the two gases meet, they form a white cloud. And this white cloud is actually found, it's found closer to B than A. So I didn't write properly, but it's found, this white smoke, you can see that it's closer to B than A, sorry. And because it's closer to B, you can work out that ammonia has traveled a larger distance than the hydrogen chloride. And this basically highlights the first factor that affects the rate of diffusion, that being the relative molecular mass. So the lower the relative molecular mass of a gas, the faster the gas will diffuse. So in this case, the ammonia has a lower MR than the hydrogen chloride gas. And yeah, that's it. We're done with the first chapter, that being states of matter. I hope you at least took something away. I know this was my first video and I was really nervous, but yeah, I hope it at least gave you like a baseline for what you need to revise. And see you next time, hopefully.